Okay, hello. Here we are. We are going to go over the homework on Latin squares. Let's go. This homework is kind of easy, kind of hard. I guess it sort of depends. We begin immediately with number 2. Number 2 says, just straight away, either extremely obvious or extremely hard. Number 2 says, produce a standardized Latin square of order 5. Okay, well, alright. What does that mean? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we need a Latin square which looks like this. Alright, and now there is no instruction given as to how to do this, and honestly, you kind of just need to have some good ideas. Or try some things, or think kind of geometrically, or know things about prime numbers. And ultimately, especially because 5 is prime, it means that this sort of, all these numbers are just being kind of permuted in a sort of way. And if we want to force these rows and columns to kind of be off and to not repeat, then we can just kind of push everything over a little bit. In other words, let's just let this be 3, let this be 4, let this be 5, and let this be 1. Keep the order 1, 2, 3, 4, 5, but push everything, I guess, left 1 or something like that. In other words, 2, 3, 4, when you get to 5, you hit 1. Okay, so that's going to, of course, it's going to be a Latin square row-wise, but also column-wise, you're not going to repeat. And then, yeah, you just keep doing that, right? 5, 1, 2, sort of cycling back again, and then 4, 5, 1, 2, 3. And 5, 1, 2, 3, 4. And sure enough, this is a Latin square like magic. Woo! Okay, 3b, I think a little bit more straightforward. 3b says, take the following 2 Latin squares and determine whether they are orthogonal or not. Okay, so this is just completely straightforward activity. So we have 1, 2, 3, 2, 3, 1. 3, 1, 2, that's one Latin square, and the other one is 3, 1, 2, 2, 3, 1, 1, 2, 3. So let's go. All we have to do here is just make the ordered pairs. So, well, can I squeeze this in here? Maybe I can't. Sha-ba, ba. No, that's worse. Okay, so yeah, what have I done? Okay, and now we just stick the numbers in. It's pretty mindless. So 1, 2. You don't even really, well, okay, too late. 1, 2, 3, 2, 3. Excellent video. 2, 3, 1, 3, 1, 2, 3, 1, 2, and then 3, 1, 2, 2, 3, 1, 1, 2, 3. So you can kind of just do this in your head, but anyway, I've now done what they actually asked for, which is to construct the ordered pairs, and now we can just confirm that there are no repeats. And the simplest way to confirm that is to see that every ordered pair is represented. So there's 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And so indeed these 2 Latin squares are orthogonal. Okay, so we're just kind of confirming that a certain pair of Latin squares are orthogonal to each other. Okay. 3e, I think is a little bit harder maybe. It now says take 2, no, it's not. Take 2 Latin squares of order 4, and they're just given to you. So 1, 2, 3, 4, 2, 4, 1, 3, 3, 1, 4, 2, and 4, 3, 2, 1. That's one of them. And the other one, how have I planned this so poorly? We'll do that. 2, 3, 4, 1, 3, 4, 1, 2, 4, 1, 2, 3. Are these two Latin squares orthogonal? I cannot just tell immediately from a glance. I'll just try to do it. So I get 1, 1, 2, 2, 3, 3, and 4, 4. Well, that's convenient. Now I keep going, and okay, look. Immediately we have bad. Here's 2, 2, and so we stop. These two Latin squares are not orthogonal because the ordered pair 2, 2 has repeated. Okay, number 4 says, oh boy. Number 4 says, yo, just produce an orthogonal pair of Latin squares of order 5. Okay, well, how hard could that be? 1, 2, 3, 4, 5, and it sort of fills in partially what's supposed to go on here. And now we're just given that we're supposed to do like this. Okay. Once again, you could spend an hour on this and totally fail and be lost, or you could know immediately what to do just based on some sort of intuition or experience. So I won't say which category I fell in my first time trying this. For starters, we can just repeat the logic from before. So now I'll switch in colors. This is 3, 4, 5, 1, 3, 4, 5, 1, 2, 4, 5, 1, 2, 3, and 5, 1, 2, 3, 4. Okay, so that part was fine, but now I need to sort of force them to be orthogonal. Okay, this would have been a great time live for the very, very smart people in the class to share their thought process on this, because I can't remember what the smart people do, but I'm kind of smart. I think the sort of idea here is, and we are this is a heavy foreshadow of how Latin squares are very much related to the finite projective plane. Because I'm feeling, well, yeah, I want no ordered pairs to repeat. So what should I do? Well, basically what I'm going to do is just do everything sideways. So I'm going to continue to, and I think it doesn't even matter whether I go up or down. No, it does matter. So I kind of like this cycle pattern, but now I'm going to cycle the other way. So I don't want this to be, this should be a 5, because it can't be a 2. So 4, 3, 2, 1, like that? Is that what we're going to do? Yeah. Yeah, so we're just going to go now 5, 4, 3, 2. In other words, I've just decided to now permute in a column sense. And I guess now the direction is sort of up. So 2, 3, 4, 5, 1, 2, 3. Why is that so weird? 1, 2, 3, 4, 5, 2, 3, 4, 5, 1. Is that what I want to do? Yeah, that's right. And now 3, 4, 5. It's very bizarre to me for some reason. No. 1, 2, 4, 5, 1, 2, 3, and 5, 1, 2, 3, 4. What has happened here? Well, it's certainly a Latin square, because I just went in a row up the columns, and the part that the book had filled in for me meant that it forced everything to be offset by 1. Why is it mutually orthogonal? That is, I think, less clear. But without totally giving this away, why should these be mutually orthogonal? I cannot answer. But I'll tell you that we can just start counting stuff, and we can just confirm that this is true. Why is it true? Well, we got 1, 1. We got let's see, we got 1, 1, 2, 1, 3, 1, 4, and 1, 5. So the 1's all gone. How about the 2's? Well, we get, okay. I guess I sort of see what's going on now. Do I see what is going on now? I kind of do, yeah. So if you see what's happened here, is that if you circle all the 1's, oh man, this is very contentious. If you circle all the 1's, then somehow I have forced all those numbers to be all different. Why? I cannot say. But this pattern is going to continue to repeat. Say, for example, all of the 2's, which all lie along this diagonal, this extended diagonal, which sort of goes off the screen and kind of repeats. Well, those 2's are all going to be represented by this 1, 4, 2, 3, 5 type arrangement. And why is it always the case that I have different numbers there? I guess there is kind of a reason, right? Because when I go, let's see, because if I go up and over 1, is that the best way to think about it? Going up and over 1 is like skipping by 2. No. Shit, what's going on here? 2, 4... Okay, here we go. It's skipping by 2 but going the other way. Yeah. So here, if I'm here at 2, for example, this is so complicated. If I'm here at 2, 2 plus 2 is 4. But 4 plus 2 is 1 mod 5. Plus 2 again is 3, plus 2 again is 5. So moving in this direction down the, this would have been better live with someone smarter, but I think this is pretty good. Moving in this direction starting here, going down, and then continuing like this, adds 2 every time. Why does it add 2 every time? Well, that's 2 every time because why is it doing that? Oh man. Because I have both, well, because on the one hand, the number to the remember it's the black numbers that were filled in initially, and from here to here, it sort of got, well, okay. This 2 is 2 above the 5, because the 4 is 1 above the 5, and the 2 is 1 above the 4. What the hell am I trying to say? I'm saying that the black numbers along this main diagonal, where it was built in that this number is up 1 row higher. I know what I'm talking about, but I can't articulate it. Let's just do one more. In blue, take the 3's, for example. Where are the 3's? They're here and here. And why must the 3, so this is now 1, 3, and this is this. Okay, why must, and confirm, we're just confirming now that these are mutually orthogonal. And now, once again, we skip by 2. Starting at 1, plus 2 is 3, plus 2 again is 5, plus 2 again is 2, because 5, 1, 2, plus 2 again is 4. And so, okay, a better explanation is possible here, but anyway, we did the job. Good, moving on. This is something we can talk about in our Zoom call, and someone can share their understanding. Oh, number 7 is just totally silly. I probably should not have assigned it. It just says, prove that if you swap any 2 rows in a Latin square, or any 2 columns in a Latin square, it's still a Latin square. Okay. Duh. That's all I gotta say about that. We discussed this in in the video, in fact. Okay, this leaves 2 problems. This is a nice short homework. These 2 problems are 3 problems, 9, 12, and 13, but it's really just 2 problems because 12 and 13 are sort of the same problem, or 13 is the continuation of 12. So okay, what's number 9? Classic application of Latin squares. Here we go. We are given some, what's going on here? Some nurses. You are a nursing supervisor in a small nursing home, and we are trying to schedule the 4 duty nurses. Okay, so there are 4 nurses. Their names are W, X, Y, and Z. Gossett names them, but never mind. And we're trying to make a plan for the next 4 weeks. So for the next 4 weeks, we need a plan. I seem to vaguely recall myself. Well, okay. Yeah. There are 6 4-hour shifts: morning, afternoon, evening, and graveyard. Okay, so I'll tell you the way this actually works is that people's sleep schedule kind of adjusts after a couple of days, and so if you're going to be always working the graveyard shift, for example, then they have you do that for a certain number of days in a row. You don't just work the graveyard shift one day and then work in the morning the next day. You work, in fact, this is the way they do it in like med school and stuff. They have you do the overnight shifts like every day for like 2 weeks, and then not again for a really long time. So we're going to schedule this for the next 4 weeks. We're going to do one thing for a week, and then et cetera, et cetera. Okay. She intends to schedule every nurse to work every shift for a 1-week period. Decide a fair, sign a for the 4 weeks. The roster should be expressed in terms of the. Okay. So all right, maybe this is just not so hard, right? We have the 4 nurses. So let's call these nurses X, Y, Z, and W. And we have the they are already named that. So let's decide. Yeah, I think maybe this is the better way to put it. So take morning, afternoon, evening, and graveyard. What's going to happen during week 1, week 2, week 3, and week 4? And well, it's completely arbitrary who does what in week 1. So in week 1, let's let the W nurse work in the morning, and then X in the afternoon, and Y in the evening, and Z in the graveyard shift. And then of course what we want to now do is just make a Latin square with respect to W, X, Y, and Z. And this is why I think, so the true Latin square of order 4 is going to be the one enclosing this box. And that's why I think Gossett's description of it being based in numbers is a little bit too restrictive, because of course it's still a Latin square, even though the entries in this case are letters. Okay, anyway, the specific problem says she wants to be fair. This is the nursing supervisor, so she intends to schedule every nurse to work every shift for a 1-week period. And so maybe everyone hates the graveyard shift, so everyone's going to do it once, everyone's going to do morning once, etc. So that seems like the fair thing to do. Okay, so we just need to finish off this Latin square. There's really not much to say here, except you got to be a little smooth, because like Z's been working the graveyard shift, so Z has to just go home now and sleep. So when week 2 starts, you don't want a nurse Z starting right in the morning. In other words, they can't work shifts back to back. In fact, I think Z should get to go home and sleep it off as much as possible. And then in the transition from week 1 to week 2, Z should work the evening shift. So Z can sleep all morning. And the same sort of logic now applies. That, and so we get Z, so W, X, Y, Z, so it should go W, X, Y, Does this make sense? Yes, because what it means is everyone gets to go home in between week 1 and week 2 and have 12 hours, I guess, off before their next shift begins, right? Because X works the afternoon shift on the last day of week 1 and then has the evening and graveyard shift off and then can show up early in the morning and same thing. Alright, anyway, so now at this point we just kind of keep permuting this. So it's just going to go Y, Z, X, W, no, WX. Why am I having trouble with W, X, Y, Z, W, W. There we go. Once again, X should not have to, well, okay, at this point we can just fill it out. This is Y, and this will be W, and this is Z. Okay, so there you go. That wasn't a great explanation. So this is, yeah, as I said, week 1, week 2, week 4. Okay, the last problem is like the real problem for this whole section, so to speak. Well, there were these kind of challenging math problems, but now this is the problem that is using the full power of the Latin square. So here we go. We are a soap. This is numbers 12 and 13. We are soap manufacturers. This is almost exactly like what we did in the video. So hopefully this was okay. We wish to develop a new detergent that causes less environmental damage than the old detergent. The new detergent should also work well at various kinds of cleaning. The researchers at the company have 4 candidate detergents, codenamed A, B, C, and D. So, I mean, this is just exactly like what we did in the video. The 4 detergents are A, B, C, and D. And they wish to test them with 4 kinds of cleaning tasks. Normal, oh man, cleaning tasks. And the normal thing, there's normal soiled clothes, grease stains, alright, food stains, and mud stains. So these are the 4 kinds of cleaning tasks that we are going to ask our 4 detergents to show that they can work with. And we have 4 different brands of washing machine because we want to see if the washing machines are a factor, and the washing machines are X, Y, Z, W, or W, X, Y, and Z. Okay. And management has decided that doing tests with all 64 combinations is too expensive because that's how many you would need, right? A can be paired with each of these 4, B can be paired with each of these 4, so there are 16 combinations. If you're only testing detergents and cleaning tasks, but then for every one of those 16, there are 4 different washing machines, so you would need 64 tests to test every possible combination. Instead, they say, or just design a fair testing arrangement that exposes each candidate detergent to each washer brand and each type of cleaning task. Okay. So, yeah, I think now we know what to do, and what we need to do is to make a Latin square. And specifically, we can think of the detergents, A, B, C, and D in a grid, and the N, G, F, M being the 4 cleaning tasks. And well, we already want to test, of course, each of the detergents against each of the 4 cleaning tasks. And so the question is only, how do we integrate the washing machines into it? And actually, it's a little interesting because Gossett says, his exact quote is, design a fair testing arrangement that exposes each candidate detergent to each washer brand and each type of cleaning task. Each washer brand, each type of cleaning task. So we already are going to expose each detergent to each kind of, automatically, however we fill in this chart, we will have exposed each kind of detergent to each kind of cleaning task. But if you interpret what he says literally, exposes each candidate detergent to each washing, so we have to expose each detergent to each type of oh my god, each can detergent, each washing brand. So we need, each detergent needs to be matched with each washing brand, a washing machine brand. So if you just did like WXYZ, WXYZ, etc., like this, you would have technically met the constraints of the problem, I think, because he specifically only asks each detergent to be matched with each type of cleaning task and each type of washing machine. But then he threw in this word fair. I don't think this is a fair way to do it, because we are consistently testing washing machine W on whatever N was, normal, whereas we're consistently testing washing machine X on grease stains. So this does not seem like a good idea. And so instead, in order for the testing to be fair, we would like to test not only each washing machine with, not only each detergent with each type of cleaning task, and not only each type of detergent with each type of washing machine, which is to say that W, X, Y, and Z should appear in each row, but also we would like to test each kind of washing machine with each kind of different cleaning task, which is to say that W, X, Y, and Z should appear in each column as well, which is to say that this should be a Latin square. And so how to do this Latin square? Well, it doesn't matter, you have a lot of choices. So this is one of them. So W, Z, Y, Z, W, X, and Y, X, W is one way I did it. Okay, so that ends problem 12, and then comes problem 13. And problem 13 says, oh, I got another parameter. And another thing is water hardness, denoted H1, H2, H3, and H4. And now specifically, we're only going to do 16 tests. So how can we do this? Okay, this is exactly like what happened in the video. And so now we have 4 levels of water hardness. Water hardness. And it's kind of amazing somehow that you can actually do this. Let's call the 4 levels of water hardness 1, 2, 3, 4. We can, in fact, with just 16 trials, we can test every single one of these properties with respect to every single other property in a pairwise manner. Okay, and what we need right now, if you're kind of experienced with this, what we need right now is a set of 3 mutually orthogonal Latin squares of order 4. Okay, so I think when I did this problem myself some number of years ago, I just opened up Gossett to the section and just kind of copied his Latin squares. But I think it's only fair to sort of on the spot come up with a set of 3 mutually orthogonal Latin squares of order 4. Let's do it. So I will begin just kind of like in the video. Sure, how will I do this? Maybe I'll do it kind of here. Okay, so 1, 2, 3, 4. So I may always have my Latin squares in such a way that they begin with 1, 2, 3, 4. And so now I'll do 1, 2, 3, 4. In other words, I'll let this be the standardized Latin square of order 4. And in the video of the lesson, we showed that there are exactly 4 of these. So I will do, I'll take one of them, which this might have been the first one actually. So you let that be a 1, and then that has to be a 4, and that has to be a 3, and that has to be a 4, and that has to be a 3. And then you're free again to choose what to do. So just for symmetry purposes, I'll do that. Alright, so I think it's not too hard to just make a Latin square. I've made it standardized, and now we're going to finish it off from here, sort of live, so to speak. How can I make 2 more Latin squares which are orthogonal, each orthogonal to this one? Okay, well, let's go. First of all, note. So I'm going to just make this Latin square first, and I'm going to construct it in such a way that it's orthogonal to this one. And because 1 is matched with 1, 2 is matched with 2, 3 is matched with 3, and 4 is matched with 4, it means that those 4 ordered pairs, 1, 1, 2, 2, 3, 3, 4, 4, are already used. Okay, so now what should go here? Well, of course it can't be a 1 because it has to be a Latin square. It can't be a 2 because 2, 2 would be a repeat of an ordered pair that we've already seen. So it has to be a 3 or a 4, and I see no particular reason to do one or the other, so I'll just make this a 3. Okay, I'm just going to put this thing down. So if that's a 3, now what? I claim that, so this choice was arbitrary, this 3, but I claim that now I think there are going to be no more choices. And this gets a little bit subtle, so let's try this. Let's see. What can go here? Well, it can be either a 2 or a 4, seemingly. What can go here? Well, also seemingly a 2 or a 4. But if I put a 4 here, then that would be 4, 4, repeating my ordered pair 4, 4 that already exists. So that can't be a 4. So that, in fact, has to be a 2, making that a 4. Now I go here. What could go here? Well, of course, it can't be a 3 or a 2, so it's got to be a 1 or a 4. But it can't be a 1, because if it were a 1, then I would have an ordered pair 1, 1, repeating my ordered pair 1, 1 that already exists. And so it must be a 4. And what else? Well, now I think am I almost done? What could go here? Don't know. Let's see, could it be it seemingly could be a 3 or a 1, but if it were, let's see, do I have any repeats now? I have a 1, 4, and a, oh boy, I have a 1, 4, that's it, right? 1, 4, 3, 4, 4, 2. 1, 4, 3, 4, 4, 2. So now what, lost kind of my train of thought, I think, a little bit. What could go here, maybe we want to do? It's either going to be a 1 or a 3. Yeah, down here. This is going to be either a 1 or a 3, because 2 and 4 are used already in this column. But it can't be a 3, because if it were a 3, then I would have a 3, 3 ordered pair, but that would be a repeat from the first row. This has to be a 1, so it has to be a 3. Now, are we finally done? Come on. Let's see, if I go here, there's already a 4 and a 2 and a 1, so that has to be a 3. So that has to be a 4. Oh man. What could go here? How am I still doing this problem? Could this be a 1? If it were a 1, there would be a 4. If it were a 2, then there would be a 4, 2, but there's already a 4, 2. So it can't be a 2, so this has to be a 1, so that has to be a 2, so that has to be a 2, and that has to be a 1. Oh man, that was, I think, kind of hard, I think. Okay, one more.